Bristol, who's going to tell us about realizations of rigid graphs in other geometries. Whenever you're ready.
Hi. So thanks for having me. This is going to be, oh, there we go. This is going to be joint work with Georg. This has been in, I think if any of you went to ILAS last year, this is kind of improved results on this. Basically because this word used to say minimally rigid and now it says rigid. So that's a step in the correct direction. So, right. So I'm just going to mention some brief stuff about complex realizations. So you can kind of just assume everything works. So all I'm doing is, instead of doing d-dimensional framework, I'm now doing, or d-dimensional realization, I'm now doing d-dimensional complex realizations. So you just allow it to have complex coordinates. You have to be a little bit careful. So you define your rigidity map like so, but this is not a metric, this is a quadratic form. So you end up with some weird stuff going on. For instance, in the quadratic form, your unit ball, for lack of a better word, is no longer compact, so that can make some sort of weird stuff happen, but it's a nice way of extending the problem to the complex numbers and keeping everything nice and algebraic, so you can still use all your lovely algebraic geometry. So that's just a setup of the map. We're just going to say that two things are equivalent if their rigidity map gives the same value. And we say they're congruent if there is a isometry. This is an isometry of quadratic forms. You don't have to worry about it too much. It means that they have the same length edges. It's actually an equivalent thing. Yeah, we're going to say they're congruent if you can map one to the other. Okay? Right, so this is complex realizations. The next one I want to kind of mention, because we're doing planar and spherical, is exactly the same stuff, but spherical realizations. So in this case, we're looking at the complex sphere, so the complexification of the sphere, however you want to think about it. Worth thinking about, like I said, that this thing is going to be non-compact, okay? We now look at complex spherical realizations, so just realizations that lie on the complex sphere. We have the same map, but we're just restricting ourselves to only looking at spherical realizations, which can be rewritten in a kind of nicer way, because everything's distance 1 away from the center, so you can just play around with the algebra to get that. And you can yet again say they're equivalent if they give the same edge lengths, and they're congruent if there's an isometry that maps one to the other. So this isometry will just be a linear isometry in the previous sense of the word. Is that fine with everyone? I hope. Cool. Right. So there's reasons why we go to this setting. So, firstly, quickly, we're going to say a graph is rigid if almost all of its realizations have a finite set of equivalent realizations congruent, modulo these congruences. And we're going to say it's spherical rigid if you do the same thing, but just do spherical realizations. Okay. And it's just kind of a well-known result that spherical d-rigidity and d-rigidity are exactly the same thing. So I've called it spherical d-rigidity. I will never call it that again. That is just a one-off, so I could differentiate the two, but they are exactly the same. Okay. These definitions are all equivalent to real rigidity counterparts, so any sort of idea you have about graph rigidity is also correct here. Nothing crazy is happening. I've just defined it in a slightly weirder way by just doing complex solutions, but that's it. Nothing has changed. Okay. So why are we looking at complex solutions? Because we live in a real world, theoretically. We want to count, for God's sake, right. We want to count realization numbers. I'll come back to that slide later. So kind of a well-known thing when you're doing with real solutions of, say, polynomials and stuff, it's not really a generic thing. So, for example, take a parabola, okay? So this is going to be x squared plus c. And the C is going to kind of be determined by this line. Okay? So it's some number. Now, how many solutions does this have? Well, as I vary C, it has 2 solutions, 2 solutions, 2 solutions, 1 solution, then 0 solutions. But consistently, it has 2 complex solutions apart from some kind of small set of problems. Well, this has a very large set of problems. So down here is a problem, and there's no way around it. So it's always sensible to go to complex when you want to get an upper bound on your number of real realizations. And you can kind of prove that these realization numbers, they still work for real realizations. So there'll be a nice open dense set of real realizations with this many, exactly this many complex equivalent realizations. But regardless, what we're interested in is realization numbers. This just comes from the observation that the cardinality of this set is the same for basically almost all points. So you can just say the realization number is exactly this set. You just define it by choosing almost all points and make that your number. And you do the same for spherical. Okay, I'm quickly going to skip back to also mention this construct, coning. So if you have a rigid graph, you can always cone it by adding an extra vertex, connecting it to everything else. That will preserve rigidity. And this is quite a well-known result from Walter Whiteley. Most important part about this is just, that's what coning is. It kind of takes you 1 dimension up. And that's my notation for coning. So they're the 2 things you should take away from this slide. Okay, so these realization numbers, when can we compute them? So you can compute them when d equals 1. It's quite easy. There's a nice short proof you can do to prove it's about kind of bi-connected components, and you just count them. D equals 2 is already a nightmare, but there are algorithms for minimally 2 rigid graphs. You can compute their realization numbers. This involves the kind of, the algorithm is kind of almost like a minor decomposition. It's more complicated than that, which means it's kind of an exponential kind of size in some sense. You end up with lots and lots of prop cases, and you have to add them all together. So the algorithm is already exponential, or maybe double exponential, I can't remember. So it's a slow algorithm. And then for general 2 rigid graphs, d-rigid graphs, there's no algorithm. You have to use Grosvenor basis, but that's not actually kind of correct, because what you're effectively doing is you're saying you pick a random set of edge lengths in some sense and do it. So the whole algorithm is not deterministic, it's probabilistic. And it's still, even worse, it's really slow. So they're really hard to compute these things. So if anyone wants a pet project, just working on this is a good idea. But we can do the 2 realization number of minimally 2 rigid graphs, and we can do the spherical 2 realization number of minimally 2 rigid graphs. Okay, so when computing them, we notice this. So this is for the minimally 2 rigid graphs with 12 vertices and minimum degree 3. The minimum degree 3 is just kind of, if you have a minimum degree 2, that just doubles the number of spherical and the number of real, the normal ones, so it doesn't really matter. But the observation is that this line is the y equals x line, and everything lies above it. And it kind of like shoots off a bit weird in some sense. And this is just when you plot them against each other. And why is this? Why is this true? So we proved it. We proved that this is indeed true here. Okay? But first, because I forgot about this slide, here's an example. This is the smallest example where the 2 numbers differ. So it's the 3-prism graph. It has 12 equivalent realizations. Here are 12 real ones. You can actually make them all real. And there's 16 realizations on the sphere. So its 2 realization number is 12. Its spherical 2 realization number is 16. Those 2 numbers are clearly different. So this number can actually differ. And this is an example where it happens. But yeah, we proved 2 things. So we first proved that if you have a d-rigid graph, coning it just gives you, in d+1 dimensions, the same number of realizations that you would get on the d-dimensional sphere. This kind of makes sense, right? because your picture is going to look something like so. You have a point at the origin. You're going to have your graph living on your sphere. It's going to be connected like this. And you have your distances like this. And when you project out, it effectively doesn't really make a difference in some sense. That's kind of the argument. It's not exactly like that, but it's basically it. More surprisingly is this one. And I'm going to briefly talk through the proof on this. So, to prove it, we're first going to assume that our theorem is true, our top theorem. And we're going to use that. That means that we don't have to talk about spherical realizations. We can just talk about coned realizations straight away. Okay. So what we're going to do is we're going to think, what does a coned realization really look like? So a generic one is going to have a point somewhere, the points, other points are going to be elsewhere. Okay. What does the d-dimensional realization of the original graph look like? Well, what it kind of looks like is you've restricted yourself to a d-dimensional linear space, but then you've put the cone vertex at infinity in some sense. It's no longer a kind of a distance constraint, it's become like a linear constraint. But this doesn't really work. It doesn't really, in some sense, make sort of sense when you're building the equations. So there's an issue. So you just do the kind of really dumb thing and then just invert the last coordinate of your point at infinity. So your cone vertex is now going to be at this point 0, 0, 0, 0, 0, infinity. And you just say, okay, it's actually at all zeros. And whenever I put the last coordinate in, I invert it in some sense when I do the distance. Okay, but this still kind of doesn't really make any sense. So you kind of have to correct your rigidity map to allow this to kind of occur and occur in a nice way. And once you've done this correction, you've built a new rigidity map where it has like this inverted coordinate. It plays well with just kind of normal generic realizations of the coning. But importantly, it allows you to approximate your cone framework with all the points in the plane and one point at infinity by a sequence of generic realizations in d+1 dimensions. And this kind of then plays with the nice property of these realization numbers. So when you look at a realization, as long as it's regular, so it has some nice behavior when it comes to its infinitesimal rigidity and so on and so forth. So you could use, for instance, that it's infinitesimally rigid and everything equivalent to it is infinitesimally rigid, for example. If you have something like that and you approximate it via generic realizations, then the number of realizations of your first one, the non-generic, is upper bounded by the number of realizations for the generic ones. But we already know the generic ones. We already know that they are exactly the realization number. That's the idea. QED proof. Why I mention this in more detail is because this idea, it can work for other algebraic information. So we're just using the idea that kind of the realization number of a given realization, the number of equivalent realizations, is kind of like lower semi-continuous, and it behaves well with nice regular values and stuff. If you can think of anything else that works well with that sort of thing, you can use this exact same construction and just plug that in and it'll still work. So if anyone has any nice algebraic geometry constructions they want to use, this sort of method will prove that you'll get more or maybe less, depending if you're doing lower semi-continuous or upper semi-continuous, with the sphere compared to the plane. That's roughly the idea I want to kind of get across. A lot of coning before has just worked well with linear, like the linear ideas of stresses and equilibrium things. This works well with algebraic kind of non-linear properties. And that's kind of the main takeaway you should take from this. Okay. Getting into computational stuff. I'm just going to briefly define some stuff. So we've defined theta to be equal to this, the spherical realization number divided by the realization number. We're assuming the graph is minimally d-rigid with m vertices. The reason for that is everything we did here was with d equals 2. And we need to be able to compute it to say anything interesting. And the only thing we can compute is d equals 2. So that's unfortunately why that's like that. We also did the maximum. By our theorem, the minimum is bigger than 1, and you can find ones with the minimum is equal to 1. Just take any sort of nice caudal graph. That'll do the trick. So any D tree will have that this ratio is equal to exactly 1. So the minimum is basically boring. We only care about the maximum. You can prove that this ratio has to be bounded by some sort of exponential. This alpha has to be bigger than or equal to 1. This is just taken as, yeah, just from how I defined it. But we also want to kind of look at this minimum value of alpha, so this alpha d. I'm being a bit cautious here. I'm just saying it's the minimum value so that this is true for every alpha that's strictly bigger than alpha d, just to be on the safe side. It's quite easy to check that alpha 1 equals 1 for d equals 1. We think it's true for d greater than 1. I'm just going to prove it for d equals 2. We don't have any computational methods for dealing with d equals 3, d equals 4, d equals 5, so on and so forth. In some sense, you don't really need it. What you need is a way to do this for our graph. So compute the d spherical realization number and the d realization number for a graph. And once you have one graph, you can kind of glue things together to get all the graphs. But this is a current conjecture, still open, apart from the d equals 2 case. So we've managed to prove asymptotically that this, or prove that this alpha 2 is between 1.1139 and less than or equal to 3.4642. The upper bound just holds from some nice results from Bartos, Emeris, and Zasmos, where they gave an upper bound on the number of spherical realizations. They also then gave an upper bound for the number of planar realizations at the same time. Not using our result just because the method just gives an upper bound for both. And what you do is you just take that upper bound and then you say, okay, I'm assuming that the 2 spherical realization number is as high as possible and it's divided by what is as low as possible. What's the lowest it could possibly be? 2. That is actually the only known lower bound on this. We can't actually improve that at the moment. If you can improve it to being bigger than 2 to the n minus 3, this 3.4642 will half effectively. So we think the number is probably, alpha 2 is probably between 1.1 blah, 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 and 1.7321. That's what we believe. By the way, the lower bound is just achieved from this graph, and you glue copies of it along this triangle, and that gives you an asymptotic construction to get the lower bound. This isn't actually the, you kind of end up with a weird one here because you want to get the ratio to be good. So it's actually, and it also has the ratio and how it glues and how many vertices it has outside of it. This graph seems to be the best. There are other graphs with a bigger ratio, but they don't glue as nice, effectively, which is kind of a bit odd. But so you can find graphs where the ratio is bigger, but this one just glues together best. Okay. That's basically it. So a very short talk. So thank you for listening.